Okay, so last week on Wednesday, when we were talking about enantiomers, diastereomers, I got a little bit ahead of myself because that's actually the practical how you determine if things are diastereomers, enantiomers, etc. is Wednesday's lecture video. So when I handed you the problems and everybody was kind of floundering around to try and figure that out, that's what Wednesday's video is about. There is also video online to take Newman projections and make them into Fisher projections. And there's an online quiz, and that will be all that will be due for Wednesday. Okay, so that's for Wednesday. I have all the graded stuff graded. It's outside my office. Scores are in Canvas. The only scores that aren't in Canvas are Sapling Chapter 3-4, which I have to put in. Midterm grades are due on Wednesday. I'm obligated to give grades to people I need to give grades to, and it comes up and says you need to give grades to these people, or C minuses or lower. So if you don't get a midterm grade, then you're not one of those two people. You got a C or higher, and you'd be able to see what your grade is because the percentage is automatically updated. So the only thing for Wednesday is watch the video and then do the online quiz, and then we'll do some problems or talk about on Wednesday. And that's also Friday. We'll do also RS problems and enantiomer, diastereomer, same meso, etc. Online quiz should be a piece of cake because we did some of that last Wednesday. Okay, so what I had planned on doing today then was talk a little bit about rotation, enantiomers, diastereomers, a little more practical stuff as the day back. These slides are online, but I did not print them out because they would have sent the photocopier over the edge. And as much as I'd like to do that and get it to destroy it and get a new one, it just would have frustrated me and sent me over the edge, which doesn't take much. So they're online. There's only a couple things that you may want to take notes on as we go along. So we talked last week about enantiomers, diastereomers, basic definitions, as well as what's different between the two. One of the things we said was specific rotation. So as far as the specific rotation goes, the only thing we dealt with was whether or not when you put a chiral molecule in the path of plane polarized light, the plane polarized light gets bent, gets rotated either clockwise, counterclockwise, clockwise D, counterclockwise L, two enantiomers, opposite directions. Now what we want to talk about is the specific number of degrees that get rotated. That's going to be the important part. But what do I mean by chiral molecule? I mean a molecule that has a left-handed and a right-handed form, or a D and an L. So in order to do that, in order to be that chiral molecule, that one enantiomer, it needs chiral centers, and it cannot be meso. Okay, so we've got one of the two enantiomers. So when we put the chiral molecules in plane polarized light, it rotates by a certain number of degrees. Let's talk a little bit about that. That is a specific physical property of an enantiomer. And I'll relate it to stuff that we've kind of talked about along the way. So, first thing is, this is observed rotation. Alpha is in degrees. And we're going to measure alpha in lab on 3 separate occasions coming up. So, what does that experimental rotation, what's it dependent on? Well, the exact compound. The length of the sample cell, the concentration of the sample cell, and the solvent. Now, the two things in black we can't really control. There's not much of a solvent dependence on optical rotation. You can use pretty much the same solvent and get the same rotation. The length of the cell, though, plays a role, and so does the concentration. So ultimately what we want to build up to is specific rotation, the exact number of degrees, positive or negative, as a specific chemical or as a specific physical property of a molecule. So that if I had a glucose sample and I wanted to know how pure it was, I could measure its rotation and tell how pure it was, or even tell that it was glucose. So let's deal with cell length first. So as far as cell length goes, it's a direct relationship between cell length and that number of degrees. So you double the cell length, you double the number of degrees that it rotates. Kind of makes sense. You double the cell length, you've doubled the number of molecules that come in contact with the plane polarized light, you've doubled the rotation. It's a direct relationship. So if you use a different cell than somebody else, you're going to get a different rotation. So we're going to have to take that into account. We could dictate to everybody that you need to use this length of cell, but we really don't. So we have to take that into account. Right? So double length, double the number of molecules, double the rotation. If you got molecules, double the concentration of the molecules, twice as many come in contact with the plane polarized light, and that rotates then twice as much. So it's another direct relationship. Again, we could specify a concentration. We could say, use this concentration, but we don't do that. So each person, depending on the concentration and the cell length, might get a different rotation for a molecule. So what people decided to do was they decided to come up with what is called the specific rotation and make this a standard physical property. So here's the specific rotation. Specific rotation is alpha in brackets with a D and a temperature. So when you see the alpha by itself, that's the number of degrees that you're getting from the instrument, which is called a polarimeter. And the temperature, and then what's D? D is a very specific wavelength of light. It's called the D line of sodium. So most of these instruments use a sodium vapor lamp, which used to be the street lights, all had kind of an orange glow to them. That's a sodium vapor lamp. So really, this is just a specific wavelength. Temperature does not affect the optical rotation very much, if at all. It's not refractive index. Refractive index you can correct for. There's no correction here because 20-25 degrees, it's pretty similar. So this specific rotation we calculate by taking our experimental rotation, our cell length, and our concentration. So this is not that. Okay, pen. This is our experimental rotation. And then this is our cell length. And this is our concentration. So basically what I'm doing is I'm normalizing this specific rotation for cell length and concentration. The only question is units. So the specific rotation is in degrees. The cell length historically is in decimeters. Why am I writing at an angle? So the cell length is in decimeters, and because organic chemists apparently don't like math, it's a 1 decimeter cell, bless you. So that makes the math easy. Now 1 decimeter is 10 centimeters. So the instrument that we have in our instrument room that we're going to use a couple of times in lab has actually a 1.1 decimeter cell. Well, yeah. But you'll find that out in lab because that's a number you're going to have to divide things by. But it's basically a 10 centimeter cell. And ours is a very old one that takes a lot of solution to make the measurement. I have in the past used ones where the cell length are much smaller and you can get away with a milliliter. But this one takes a lot more than that. So that's the cell length. Concentration is not in molar units. It's in grams per milliliter. And the reason for that is a lot of times we measure optical rotation or specific rotation and we don't know what the compound is. If we don't know what it is, we don't know what its formula is, we don't know what its molecular weight is. But what we do know is so many grams per milliliter. So that's the typical units that we use. So that gives us a specific rotation. So the idea here is that that specific rotation then is a physical property of that molecule. So that if I had a glucose sample and I wanted to know if it was glucose, I could compare its specific rotation to the literature value. And that would give me some other physical property. It also will allow us to judge, well, number one, the sign, whether it's D or L, and then also whether or not it's 100% D, 90% D, 50% D, etc. And that's the next thing that we'll look at. So there are questions for this on sampling, calculating it, so that's part of the reason why I'm doing this. Okay, let's go forward. Forward. That was backwards. Forwards. So let's look at a specific example. This is the one we're going to do in lab. There are lots of chiral drugs out there. I think last Monday, somebody in the morning class had asked, so what's the big deal about plain polarized light? Doesn't seem to be relevant. Well, that's what today's lecture is sort of about. But one of the cheaper drugs that you may come in contact with that is chiral is Aleve. So Aleve's generic name is naproxen sodium. And it is this structure, and we're going to actually take Aleve tablets, isolate that compound, determine its optical rotation in lab. Then this is a carboxylic acid part, and that's a deprotonated one. Sort of like what you did with the aspirin in lab, deprotonating it and then you reprotonated it. Well, when this stuff hits your stomach, it reprotonates to naproxen, and so that's the actual active ingredient. There's one chiral center right there on the CH. Is a chiral center. So this is either R or S, D or L. So D and L refer to the way it rotates plane polarized light. R and S refers to the configuration of that chiral carbon. And, as I will probably say numerous times between now and the next exam, there is no formal relationship between D and L and R and S. Some D molecules have an R configuration. Some have an S configuration. So you can't tell what the exact structure is from the optical rotation. And that makes chiral drugs kind of tough to work with, because not only do you have to tell the FDA whether it rotates clockwise or counterclockwise, you have to tell them the exact three-dimensional structure. And that's a little tough. You have to use X-ray diffraction. I did a postdoc for 2 years in X-ray diffraction. I never had to do that. The guy who was the crystallographer, and what you have to do is grow little tiny crystals of this stuff, perfect crystals, not like what we grow in lab, like really perfect crystals that an X-ray beam will go through and get diffracted, and then you can figure out what the exact structure is if you're lucky. There's a whole process to that I never learned, and quite frankly don't have any ambition to learn at this point. But every drug company has to figure that out. because they have to certify that it's R and S. And in the past, those have been wrong for some drugs. So I just know that because the guy who was a crystallographer when I was a graduate student at Duke he would be like, well, this drug they sent to me and it was all wrong, and this one was all wrong. And he was old school, and everything was from scratch. And he was incredibly good at what he did and transferred zero of that knowledge onto me. So we've got a chiral molecule. And it turns out that if you look on a tablet, they will tell you that the specific rotation of that elite tablet is anywhere between minus 15.3 and minus 17. That's a huge range. So it's just for like qualitative purposes. But what can I determine from that? It's the L enantiomer. That's all I can tell. Now, why is it the L enantiomer? The L enantiomer will cure your headache. The D enantiomer has a little touches of liver toxicity. So that is not in the commercial leaf tablet. And if you are a drug company, you also have to show that when this thing hits your stomach, that chiral center doesn't switch. Because there's no sense in taking the drug and then having the bad enantiomer show up in your stomach after it's reacted with the acid.
So then what's the difference between the generic brand and the name brand?
There isn't.
Oh, okay.
There may be quality issues, but most of this stuff is regulated by the FDA. So naproxen sodium, like I won't buy the Aleve because that's kind of expensive. But I'll buy like naproxen sodium at CVS, Walmart, wherever I happen to go. So there really shouldn't be a difference. My doctor said, well, the thyroid stuff that I take is also chiral. She's like, well, the problems with thyroid medication, and this is a universal problem apparently, is getting the right dosage for people. So they're like not having too little energy but not having too much energy. And she's like, well, every generic, it has a different amount in it. And like 20% difference. And I was kind of like, really? That doesn't make sense. That seems like a lot. 20% seems like a lot of difference. So that might be the only difference. But I mean, I don't think we are not routinely, importing generics from abroad, I don't believe. I don't think we've done that yet. So there should be certain manufacturing controls in this. But this would be just used as a quick check. So when they're making the pills, pull a pill off the line, crush it up, put it in the polarimeter, make a solution out of it, put it in the polarimeter, see if you're between minus 15 and minus 17. Hopefully you are, but that's a huge range. What we're ultimately, I'll show you as we work through this, is that this isn't good enough to determine whether it's 90%, 95%, 99%, 99 point, how many ever nines the FDA requires for this. So that optical rotation can be used, but it's not good enough for that. But in the world of chiral drugs, it's a screen. It's the first screen. So this is a very inexpensive drug that is available chiral, in its chiral form, in only one chiral form. It doesn't change into the other enantiomer. This is a chiral carbon with no bonds that can be broken, so therefore it stays in that form when it gets in your stomach. All it does is just protonate that O- to an OH. And you'll see that in lab when we do this experiment. So one of the things that we can do with optical rotation is talk about what its percent enantiomeric excess is. So percent enantiomeric excess is simply the percent of the major enantiomer minus the minor enantiomer. So D minus L or L minus D, whichever one is the major enantiomer and minor one. So for instance, if I had a mixture that was 75% plus, 75% D, 25% L, I'd have a mixture that I would say has a 50% enantiomeric excess. So it's 50% in excess, one over the other. So if somebody said, well, I have a, let me make the math easy, 60. If I had a 60% enantiomeric excess, I need to find two numbers that add up to 100, but when subtracted, give me 60. 80-20. I made it easy. So the 10 enantiomeric excess is something that's used all the time. If we do a reaction and we form two enantiomers, do we form an unequal mixture? And if we do, what's the percent enantiomeric excess? For a drug, it should be 100. Right? We shouldn't have any of the minor enantiomer because there is a reason why the minor enantiomer isn't in the drug to begin with. Right? And this all goes back to the 60s and the thalidomide, where you had one enantiomer being a sedative, the other one causing birth defects. That's the worst case scenario. Okay.
How in the production do you guarantee that you only end up with one enantiomer?
Well, that's a good question. We'll go through that and talk. It's not easy.
Okay.
I'm sorry, can you just explain how you got 75 and 25?
I just made it up.
Oh.
So if I had a mixture that was 75-25, I would say that it has a 50% enantiomeric excess. Megan?
So you said that was up above that was L instead of
This one is D and this one is L.
above that.
Above
Sorry, back
that?
to the 17,
So this could be,
15, and 17.
so this is the L enantiomer
Before.
because it's negative.
It's negative.
Because it's negative. That's all I can tell you. That's all I can tell you. I don't know if it's R or S. Actually, I do, but that's in the lab handout. In order to determine whether the drug was R or S, they had to isolate it, grow little crystals, have the X-ray diffraction, figure out whether it was R or S, and then put it in the polarimeter and determine if it's plus or minus. All the part going up to the polarimeter is hard. Polarimeter is the easy part. But you got to figure out the three-dimensional structure. And that is not trivial. But there's no correlation. The key thing is, if I say it's L, I have no idea if it's R or S. It could be 50-50. It's a 50-50 shot. So this is the elite. And there is a way that you can determine the percent enantiomeric excess from the specific rotation. And this slide kind of outlines that, but I see equations. I see people's eyes glazing over because equations, organic, these two things do not go together. But there is a way to do this. Actually, going back here, if you have 50%, that's 0.5. If you multiplied that by the specific rotation, that would give you the specific rotation of the mixture. And then the only thing missing is a sign. Okay. So what we normally do is, if we know what the specific rotation of our mixture is, and we know what the specific rotation should be for either enantiomer, we could divide that specific rotation over the specific rotation of the pure substance, and then determine the fraction. And then we've got to figure out what two numbers add up to 1. When they subtract, give you that number, and then that gives you the percent enantiomeric excess. Well, you get the percent enantiomeric excess from the calculation, then you got to figure out what it is from there. Notice that if it was 50-50, if it's racemic, that's 0. 0 times specific rotation is 0. So that's where the idea of the specific or of the racemic mixture having a specific rotation of 0 comes from. Okay, so we won't solve those two equations simultaneously. There are many ways to do that. You could probably use the old whatever those things are called between the lines. Matrix, you use matrix method if you wanted to. If you've taken linear algebra. We'll pass on that. So, let's talk a little bit about enantiomers and diastereomers. And I ultimately will make to the question of, if you have a chiral drug and you've got to show that it's 99 point something % pure, how do you do that? Well, specific rotation isn't the way to do it. There's too many errors in specific rotation to get you to the difference between 99 and 99.5%. There's too much error in specific rotation to do that. But let's talk a little bit about diastereomers. So what did we say about diastereomers last week? How did we define them? Non-superimposable, non-mirror image isomers. How do you know two molecules are diastereomers? At least one chiral center is the same configuration, and at least one chiral center has opposite configuration. Okay? Here's examples of diastereomers. Now, what do we know about enantiomers? Enantiomers have exactly the same physical properties except one. How they rotate plane polarized light, which is useless in terms of separating the mixture. It'll tell me whether it's D or L, but that's about it. It's not that useless. But it doesn't help me separate, because every single physical property is the same. Put them on a TLC plate, you get one spot. Put two enantiomers in a GC, you get one peak. They have exactly the same physical properties. Enantiomers have exactly the same chemical properties except when? They react with another chiral molecule. So they only differ in their chemical properties when they react with another single chiral molecule. Diastereomers, completely different molecules. Different chemical, different physical properties. They can be separated by recrystallization, GC, PLC, column chromatography. They are different molecules. Sometimes two diastereomers have very similar physical properties, but they're not exactly the same. Here's two examples. These were, well, one is still sort of an over-the-counter drug. The other one's been banned. Pseudoephedrine, Sudafed, has two chiral centers, one with the OH and one with the nitrogen. Ephedrine, same thing. Looking at pseudoephedrine, we've got one chiral center with the methyl group, is the same in both cases. The one with the OH, opposite, diastereomers. So pseudoephedrine is the one that you would take if you have a stuffed up nose, a little bit of a stimulant, antihistamine. You got to go to the pharmacist and give them your ID and your driver's license. You only can buy 3.5 grams a day under federal law, because otherwise you are suspected as being a methamphetamine producer. Okay, and the only place that's good is on TV and Breaking Bad. It's not good anywhere else. Okay, so there's restrictions on that. Big restrictions on it. The one that you can actually buy over the counter, I believe, is missing that methyl group. It's called phenylephrine or phenethyl something. Different molecule, doesn't do the same thing. Ephedrine was used in weight loss formulas. A few years ago, they banned it. It's a stimulant. Take too much, your heart races. Eventually you have a heart attack and die. So it was banned. These are two diastereomers. One melts at 58-59. Ephedrine melts at 37-39. There's examples. If you put these into a GC, two different peaks. If you put them on a TLC plate, two different peaks. Or two different things. So they're two totally different molecules. Bless you. So diastereomers have different physical properties and can be separated. Enantiomers can't. So the question then becomes, I want to separate enantiomers. How do I do it? Well, if I want to separate enantiomers, I have to convert them to diastereomers. And then they have different physical properties, so I can separate them. And then after I've separated them, convert the diastereomers back to enantiomers. Yeah, that's a lot of steps. But that's how it could be done. That's how it has to be done. Somehow you have to make the enantiomers into diastereomers. So the classical example that is used is what's called, or what are called Mosher esters. So Mosher came up with this idea. I don't think he won a Nobel Prize, but people will learn his name forever because he came up with this classic way to separate alcohols. So if we have two chiral alcohols, one R and one S, and I've got a racemic mixture of the two and I want to separate them out, Mosher came up with this idea. He basically found a chiral carboxylic acid that could be made and could be purified into one enantiomer. I'm going to call it R, although you'd have to verify that by determining whether that chiral center is R and S, and I'm not going to do that right at the moment. So what happened is that he took advantage of a reaction called esterification, which we will learn next semester and you'll do in lab next semester. But basically, if you take a carboxylic acid and you react it with an ester, usually with a little bit of acid as the catalyst, you will make an ester. That's called Fischer esterification. Well, what Mosher did was he came up with this chiral carboxylic acid. He would react it with the racemic mixture of alcohols. And then what he would do is he would make two esters. Now, assuming that the chiral center on the carboxylic acid part is R, that would be the same in both cases. When the R ester reacted with the R alcohol, we would form one molecule, and when it reacted with the S, it would form the other one with the S configuration. So these two are a pair of diastereomers. Because one chiral center is the same, the other chiral center is opposite. So Mosher converted the enantiomers into diastereomers. You can then separate these things by column chromatography. He actually found in some cases that one form would crystallize preferentially over the other. So he was able to separate them by fractional recrystallization. But column would be the way we would do it now. So great. He could separate the two alcohols into two diastereomers, but I want my alcohols back. So how do you do that? Again, next semester we will learn that if you take an ester, which has the carboxylic acid part and the alcohol part, and you react it with like hydroxide or base, then you can split the molecule back up into its corresponding alcohol and carboxylic acid. So he took the enantiomeric mixture of alcohol, made two diastereomic esters, separated the two, put them into two different test tubes, hydrolyzed, which is the term for converting the ester into alcohol and carboxylic acid. He then converted them back to their alcohols, and so now you have the R and the S alcohol in separate containers. So he separated them. But again, enantiomers to diastereomers, back again. Because only the diastereomers have different physical properties. So that's a classic way. There's other ways with amines. So that's how you would separate the components. So at the drug company, if they're making this chiral drug in some sort of mixture of two enantiomers, they got to figure out a way to separate them. This might be one of the ways they do it. And in theory, if you could somehow quantify the difference between those two esters, you could determine the percentage of the two alcohols to begin with. Now, as far as chiral drugs go, we got two options. We can either separate the mixture once we've made it, or ideally we'd like to make just one enantiomer and not the other. Now, that's a little trickier. Because if you're going to make one enantiomer, the rule of organic chemistry is if you want to make a chiral molecule, you need a chiral reactant. Well, chiral reactants that most people turn to are enzymes. Because biological enzymes are chiral. They exist in one-handed form. The second place in lab we're going to do optical rotation is we're going to take yeast, add some sugar to it, and ferment it to make grain alcohol. We're also going to add a compound to that mixture that some of the enzymes in yeast will take a carboxylic or a carbonyl group, C double bond O, convert it to an alcohol, making a chiral center. And so we'll isolate the product and look at how the enzymes favor one enantiomer over another. So that's the two ways that drug companies can do it, can make the chiral molecule. They either separate or they make it chiral to begin with. But even if they made it chiral to begin with, they still have to show that it's all of one enantiomer and there's no bad enantiomer in there. Okay. So that's the difference between enantiomers and diastereomers. Now let's look at an example that it gets more to the line of how would I determine my percentages of RNS, state-of-the-art method, which really isn't state-of-the-art anymore. But we can do it here. And this, so I do lots of semi-weird research, or stuff that you wouldn't necessarily consider to be, well, not traditional. One of the things that we've looked at is essential oils and perfumes, colognes using gas chromatography, mass spectrometry. You'll learn about mass spectrometry next semester in lab. The GCMS. If you've ever watched any crime show, if the case is not solved by DNA, it's solved by GCMS because it can do everything. On TV, it does it in like 2 minutes, which is unrealistic. One of the things that we looked at was linalool, an essential oil. And so we can determine with GCMS the amount of components that are in a mixture by looking at the GC. There's usually tons of those. Like the clove oil, your clove oil in lab just had 2 peaks. If I ran that on the GCMS, I would probably have like 30. Because there's much lower sensitivity and there's a lot more than just eugenol and eugenol acetate in clove oil. So that's where we use GCMS. Dr. Saporito uses it, like with his cute little frogs or whatever he uses. With all the little toxins and stuff they have in it, he figures out what's in there. So he actually has one GC of his own, and then he uses mine as well. But one of the molecules we looked at was linalool. So linalool is this molecule. It's got a chiral center with an OH methyl double bond, and then this whole group. It's found in a lot of different essential oils, and that's what you did with clove oil, is you made an essential oil, or you isolated an essential oil. There's 2 enantiomers, the 3R, and this is L, 3S, D. Well, they have different smells. And the problem with smells is that they have to be described by language. Smells do not have a physical property or physical description. They're word descriptions. So, the 3RL is flowery, fresh, and lavender-like. Whereas its enantiomer is herbaceous, musty green, having a citric note. Okay. This is one of the problems. You cannot trademark or patent a smell. Now you can patent the formulation, but there's no physical description of a smell. So those are the 2 enantiomers. Now what does that mean for our nose? Well, chemical reaction causes us to have perceptions of different smells. So that must mean that the molecules in our nose are chiral and of one enantiomer, so that these 2 chiral molecules react differently with those receptors in order to give us a different sensation of smells. Okay, and there's lots of enantiomers that have different that have different smells. But this is one. So, lots of essential oils you can find linalool. So first thing you do is you go through and you find out, okay, what essential oils have high concentrations of linalool, and you find this whole leaf and whole wood, which is a Chinese tree, both the wood itself and the leaf. The leaf is better because you can tear the leaves off. You want the wood, you got to cut the tree down. It's not 109%, that's an error. This experiment's done in instrumental analysis with other center. But these four have the highest concentration: the hoe wood, hoe leaf. Rosewood, which is a tree that's found in like Brazil and South America. It's protected. Allegedly, there's no rosewood oil that comes from there because I think that's been outlawed. Then coriander. Coriander seeds are coriander seeds. They grow up to be cilantro as a plant. So these are the four that have the top amounts of linalool. Then there's lavandin, thyme linalool. There's lavender, which is different. Petite grain, sweet basil, clary sage. Bergamot, there's a whole bunch of these things. And I know way too much about this. And I have way too many samples, just boxes of these essential oils. And I think I called somebody and they're like, what are you going to do with this? And I told them and they're like, oh, that's interesting. So what we were interested in doing was not only figuring out the percentage of linalool in each one of these essential oils, but are the enantiomeric ratios different for these? So what we did was we took our GC and we came up with a column, or we bought a column, or a guy gave me a column, that has a chiral molecule on the surface called cyclodextrin. And the cyclodextrin basically is plus. So what I have is I have a chiral molecule on the surface of my GC. So as my linalool, my plus and minus linalool come through and interact by intermolecular forces that you learned in general chemistry, we form two different diastereomers. So they separate as they move through the column. And so if you purchase one of these GCMSs for like $80,000, and you purchase a couple of supplies for it, there was like 1,000, they give you a column. So that's what the guy did, is he gave me a column. And it works fairly well. So at the drug company, this is the state of the art. This is what they're using to determine R and S percentages. So now let's take my linalool that I purchased from Fluka, which is a chemical company. It's racemic. It's synthesized. It's not from a natural source. I run it through here, and now all of a sudden, magically, I see two peaks. One is the R, one is the S. And they should be, because this is racemic, they should be 50-50. They're pretty close. Okay, it's the area under the peak, not the peak height. So they're usually within 0.5% for the racemic mixture. Then if you take what they consider to be the R enantiomer that they've purified, you look at that, you see one peak, but then I see this little tiny S over there. So it's not completely pure. Now, the drug company, that is critical.
That's no point.
That would be bad. And what you'd have to do is to go through and figure out what's the lowest detection limit you can get. Okay, but that's bordering on analytical chemistry. But it's analytical chemistry with organic molecules. So that's okay. So now we can take all of our oils and we can shoot them into the GC, and that's the technical term that we use. When I was purchasing knockoff perfumes, imposter fragrances is what they're called, which is perfectly legitimate to make. You just can't put them back in the original bottle, and you cannot claim that they are what what their imposter is. You'll see these all the time in CVS, some various like dollar stores in some places. I must have bought 30 of them one day for like $1 a piece, and the guy's like, "It's a lot of perfume. What are you going to do?" And I'm like, "Well, I'm going to shoot it into the GC." And I realized I shouldn't have used shoot in that particular place where I was purchasing them. But anyway, so here's the differences in the enantiomers. Whole leaf and whole wood are virtually all R minus. Rosewood varies. If you buy rosewood from different places, you'll see it actually, it's always an uneven mixture or uneven mixture of the two. Sometimes it'll be more R than S, sometimes it's more S than R. But it's always a mixture. And then coriander seems to be plus. It's always plus. It could be up to 80% plus. So these plants are making the molecule differently in different chiralities, which is kind of interesting in and amongst itself. From a practical standpoint, looking at this, kind of, if you're looking at products, it can tell you a lot about the source of the product. And I'm sure somewhere somebody does this, but my interest was to develop an experiment that kind of introduced all of this in instrumental analysis. I wasn't interested in telling a company that their product isn't really rosewood oil, it's whole leaf oil, although I could do that. But their lawyer probably wouldn't like that, and my lawyer wouldn't like that either. So here's the whole leaf and whole wood oil. And what you can see is it's 99.4, 99.1. And notice now I'm getting really, really significant numbers here with precision. So it's usually almost all R minus from all these different providers. I'm sure they're just buying like 55-gallon drums of this from different places. So it's hard to know what their sources are. If we go to rosewood, the rosewood oil has anywhere from 40, 45, 55. Here's a 6733. Now, 99 to 1. I suspect this is probably not rosewood oil. That's probably whole wood oil. So it's essentials, probably whole wood oil. So is the aromatherapy outlet. So is Samara Essentials. These are all online providers of essential oils. And so you can see that in these cases, most likely this is not rosewood oil. There are some in here that are actually 50-50 mixtures. This one 49.5 to 50.5. I would suspect that this company might be using synthetic linalool to supplement maybe their rosewood oil. But again, I don't make that claim because my lawyer says don't do that. And coriander has basically mostly plus, except in this case, and this may or may not be coriander oil. So you can kind of use this in a diagnostic sense. There are companies that may actually look at this and use this as a tracer to try and make sure that their products are actually authentic. But in a drug company sense, this is the level of which you can get in determining RNS. Now that would play a role. None of these essential oils are the building blocks for your high-end perfumes and colognes, which can be very pricey. Maybe not so much the colognes, but the perfumes can be. And so sourcing the materials is a huge issue. So much so that if you take what's the top most expensive perfume? Well, Chanel's are the ones. Chanel basically will make their own raw materials. They won't buy anything. They'll just make it. They'll grow the plants. They'll extract it. They do everything in-house to control the ingredients. Now, if I wanted to, I could take Chanel number 5 and I could shoot it into the GC and figure out all the little peaks, and then I could try and replicate it, which would be perfectly legitimate. There's no ethical gray area here. It's legal. But the chances of doing that with something like that are very rare because they have they control their own sources. But a lot of people do that when they're creating their fragrances. So one of the areas we did was we had all the knockoffs, we had the original, and we tried to compare and contrast which ones were close chemically, not smell-wise. I don't let the GC do the chemistry on it. I don't smell them to try and figure out whether they're the same or not. I'm not good at that. But that's where the chirality comes into play. So plants can put these things together differently. And they do. Okay, so that's kind of the practical aspects of it and what you would do state of the art. We're not going to do this in lab, but we're going to do the rotation in lab. So for Wednesday then, enantiomers, diastereomers, meso in the lecture video, the online quiz is the only thing that's due, and then we'll do problems on those on actually Wednesday and Friday.